we continue our morning session with Rob Vandenberg from CWI in Amsterdam. And we will talk about rapidly mixing Markov chain and the sharp transition in two-dimensional ising percolation.
Thank you. And of course, I also want to thank the organizers for inviting me. So this talk is about percolation, and I should say that it is about 2D, two-dimensional and dependent percolation. And in particular, I will talk about so-called ising percolation. And but it also involves Markov chain, but the Markov chain part will only become clear at the end of the talk. So at the end of the talk, I will use that a certain Markov chain converges very rapidly. But before I talk about dependent percolation, let me go back to the classical so-called Bernoulli percolation model, and I will restrict to the following lattice, which is called the square lattice. It's simply this. And also I will restrict to so-called side percolation, which means that the randomness is attached to the sides or the vertices. And what happens here is that with probability p, so each side is made, it gets the value 1 with probability p, and with probability 1 minus p, it gets the value 0. And I'm going to use colors later on, and for 1 I will use green, and for 0 I will use red. I hope that the green is visible on this board, by the way. I think there's enough contrast. So, and independently of each other, that's the classical side percolation model on the square lattice. And so on the square lattice, every vertex, as you can see, has 4 neighbors. But this percolation model on the square lattice is intimately related to a percolation model on a lattice with the same vertices, but with more edges. Namely, what you do is, so you start with a square lattice, and then you simply add all the diagonals in the squares. Okay? And so, but you have the same number of vertices. So these intersection points of the diagonals, they are not vertices. It's the same number of vertices, but now every vertex has 8 instead of 4 neighbors. And this is often called the star lattice of the square lattice. And to get an idea of this relationship between the two percolation models, it is useful to look at a little picture. So suppose that here we have green. So percolation, I should have said that, but most of you know that. And so in percolation we are interested in connected subgraphs or clusters of green sites. And in particular we are interested in whether there is an infinite green cluster. And now look at this picture. Now, and suppose that this is a finite island of green. So by definition that means that the neighbors of these points are red. So this point is red, this point is red, this is red, this is red, this is red, this is red, and this is red. And now you can see that if I follow these red vertices, then I have a kind of circuit of red vertices, but this is a circuit in terms of the star lattice, because at some places I have to go diagonal-wise. And so in other words, every finite green cluster in the ordinary lattice is surrounded by a red circuit in the star lattice. And so this already gives the idea about this relation between the percolation models on the two lattices. And indeed, the famous classical result for this model, for these models, is the following. And this was proved by, so this is a theorem, and it was proved by Rousseau, I think it was in 1981. And the theorem says that there is a critical value PC strictly between 0 and 1, such that the following holds. If we are below PC, then there's an infinite, then with probability 1, there's an infinite green cluster on the square lattice. There's no infinite green cluster on the square lattice, but there is an infinite red cluster on the star lattice. So I will write it in this way. So no percolation of green, but there is percolation, there is star percolation, that we call it star percolation of red. So there's an infinite red cluster on the star lattice with probability 1. And if P equals PC, then there is no percolation of green, and also there is no star percolation of red. And so neither of the two forms of percolation occurs. And if P is bigger than PC, then we are in the opposite situation as here, and what we will have is that we have percolation of green, but no percolation of red. And in fact, you could also write this theorem in the following way. I can summarize, well, I can replace this theorem by two phrases, in fact. And the first phrase, so equivalently, or more or less equivalently, is the following. First of all, there is no value of the parameter of P. There's no value of P such that green percolates and red star percolates. That's phrase 1. It's all these statements are with probability 1. So it means there is no P such that with positive probability there is an infinite green cluster and an infinite red star cluster. And that's phrase 1. And the other phrase, which in this talk I want to concentrate on, and that's why I call it a proposition, is that there is no interval. Let me write it. There's no interval of positive length on which we have no percolation of green and no percolation and no star percolation of red. So there's no interval of positive length on which neither of the two forms of percolation occurs.
So the quantifiers are not clear. You mean for no interval, so that for every P in that interval?
Yeah, so there's no interval with the property that on every P on that interval there's neither percolation of green nor star percolation of red. Did I write it correctly, or did I get mixed up in the logic?
So therefore it happens in only a single
It's really helpful if you try to state things positively rather than negatively.
Well, a positive statement would be that every interval of positive length contains a point on which there is percolation of green or star percolation of red.
That's so much better, thanks.
But you will see the reason why I wrote it this way.
You can pay him later.
And so as I said, these two phrases are in fact equivalent with this. And I'm going to concentrate on this proposition. And the scheme of proof of the proposition is as follows.
Sorry, one quick question.
Yeah.
So Is that statement made that way because there are many discrete p's for which it fails, or is that something you do?
No, in fact, there is only one P for which it fails, namely PC. Well, I said that these two statements are equivalent. Together with monotonicity, it would be equivalent with that. So if for some P you have percolation of green, then also for bigger values of P you would have percolation of green. And using that, if you use that, then these two statements are indeed equivalent with the theorem. But don't worry too much about it, because I'm now going to concentrate on this proposition. I have only 30 minutes, so I have to focus on certain ingredients of certain parts of the result. Now, the scheme of the proof.
Can I ask one more question? So
Yeah.
you're going to give us a different proof of Rousseau's? You just said it was equivalent to Rousseau's thing.
You will see. You will see. So the scheme of the proof is, well, roughly speaking, very roughly speaking, the proof consists of three parts. One part, part A, says that if the probability, and I write probability in this way, I write little p as a subscript to indicate the parameter. If the let me write it schematically in this way. I take an n by n box in the lattice, and then I look at the probability that there is a green path from the left to the right of this box. And if this probability is big enough, so there is some absolute constant, and I don't know what it is, let me call it 99 over 100. So don't pin me down on this number. So if this holds, then we have that green percolates. So there, with probability 1, there's an infinite green cluster on the ordinary lattice. Part B.
If there exists an n such that blah blah blah, then.
Yeah. And if there is an n such that this probability is smaller than 1 over 100, then green does not percolate. But red does percolate. And finally, part C.
And in A, red does not start percolate?
Yeah, but I'm not going to use that. And C says that if this probability of crossing this box if this is not too close to 0 or 1, and in particular if it is between those two values, if it is between 1 over 100 and 99 over 100, then the following holds. Then the derivative of this function, of this probability as a function of p, is very large. And I'm not going to make things very precise. Then this is only an idea of the proof. So then the derivative of this probability is large, and I should add if n is large. In fact, the proof showed that it's of order log n.
So C is for each fixed large n, whereas A and B are quantified if there exists an n.
Yeah, well, you could also say for A and B that for every n it is the case that if it is bigger than 99 over 100, etc. Now, why does A, B, and C together prove the proposition? And now you will see why I wrote the proposition in this way. So suppose the proposition says there's no such interval, no interval of positive length on which neither of the two percolation models percolates. Now we do it by contradiction. Suppose that there is an interval on which both percolate. Suppose that there is an interval on which neither of the two percolates. Well, when we look at A, then we see that for all n, these probabilities must be smaller than 99 over 100, otherwise green would percolate. B says we must be bigger than 1 over 100, otherwise red would star percolate. So we are in case C, which means that for all n, this probability, and for all n and for every p on this interval, the probability is between 1 over 100 and 99 over 100. But then, by the claim in C, the derivative is large. And as I said, it's of order log n. You can make it as big as you want by making n very big. But then you get a contradiction because, so if this interval, if we call it P1, P2, if everywhere on this interval the derivative is huge, then at P2 the function value would be very large. It would be bigger than 1, but that's impossible because the function is it's a probability. So that is roughly the proof. That's roughly the scheme of the proof. And now again I have to zoom in on ingredients of the proof. So there's an A, B, and C, but I'm going to zoom in on this part C. And why is part C? So let me tell the background of this claim in part C. So the background of C is a formula which is called Rousseau's formula. And Rousseau's formula says that, it says in general that if you have an event, if you have an increasing event A, and the event we are looking at here is indeed an increasing event. Increasing event means that the more green sides, the better. And so if you have a configuration which is in the event and you make some red sides green, then the event still holds. That's an increasing event. And Rousseau's formula says that for every increasing event, the derivative, the DDP of the probability of A is the expected number of so-called pivotal sides. Now, what is a pivotal side? A pivotal side, if you have a certain configuration, so a configuration of green and red sides, then you call a side pivotal for the event A, and in that configuration, if it has the property that when that side is green, A occurs, but by making it red, A does not occur. Now, what does it mean in the particular case of in the particular event we are looking at, so this crossing event? Now, in this crossing event, what does pivotality mean? So suppose that we have a vertex V here. Well, what does it mean that it's pivotal? It means that we really need V for a crossing from the left to the right. So all crossings from the left to the right go through V. So we have a situation like this. But if we make V red, then we don't have a crossing anymore. So we also, if you think about it, it means that we also have, in the star lattice, we have a path from the top to near V, and then from just below V to the bottom. So that is, so in this situation, V is pivotal for the event we are looking at. And I will...
The minimum, it's the size of a cut set, cutting off this edge from that, is it?
Pardon?
It's the size of a cut set.
Yeah, so it means that there's a cut set of size 1, and such a cut set is called a pivotal point. That's the same. So yeah. And I will leave that picture there because I'm coming back to it in a few minutes. So this is very, so, oh no, I'm not finished yet. So this, I was talking about the background of part C. Part C said that if these probabilities are between 199 over 100, then the derivative is very large. So what Rousseau did, and in fact, I didn't say that, but Rousseau's proof more or less follow the strategy of a famous result by Harry Keston in 1980. The famous, for those of you who know, is the famous result that PC equals 1/2 for bond percolation on the square lattice. And this is a different percolation model, but Rousseau followed more or less Keston's strategy, and in particular, in this part C, so what Rousseau had to do was to show that the expected number of pivotal sites is large when this probability is not too close to 0 or 1. And what he used was a kind of combinatorial geometric idea of Keston, and which works out very well for this independent percolation model, but which becomes quite messy when the percolation model, when you have a dependent percolation model. And that is in fact the main issue of this talk. So what happens if you get dependent percolation models? And in particular, I want to mention one dependent percolation model that is the ising percolation. And that was studied by Higuchi, and I'm going to say later what I mean by ising percolation. Higuchi in 1994, Higuchi proved for this ising percolation model, which is a dependent percolation model, he proved similar result as the theorem which is still on the board here. So that you have a critical value, and below you have exactly one of the two types of percolation, and above it you have the other type of percolation. And Higuchi again followed more or less the same strategy, but as I said, because of the dependencies, certain technicalities occur, and certain parts of the proof become kind of messy, and in particular it's this part which I mentioned here. And so these are remarks. And the second remark is also related to this part C. So as I said, Rousseau and Keston used some kind of combinatorial geometric construction to force many pivotal sites. But Rousseau in 1982, he put that part in a more general perspective, and he called that an approximate 0-1 law. And this approximate 0-1 law says, roughly speaking, that if you have an increasing event A, and if the maximum over all vertices I of the probability that I is pivotal is small, I'm going to write it down in a not very precise way, but just to give the idea. Then the derivative of the probability of A is large. Well, again, I should add that if the probability of A is not too close to 0 and 1.
This is in a product space?
This is on product spaces. And why is it called an approximate 0-1 law? Because it means that if for all I and P, the probability that I is pivotal with the parameter P is small, then for most values of P, the probability of A is close to 0 or close to 1. Because once it is away from 0 or 1, the derivative becomes very, very large. So maybe I should add here, so if probability A not close to 0 or 1. So it's an increasing event, so with P equals 0, the probability of A is 0. Now you raise P, and as soon as it becomes a little bit removed from 0, roughly speaking, then the derivative becomes very large, and that cannot take a long time for the same reason as I said before. So then immediately it becomes very close to 1. Now there were many extensions. So how much time do I have, Fabio?
I'm just a little confused by this statement, because doesn't Rousseau's formula say that DDP of P sub P of A is precisely the sum over I of these things that you call.
Yeah. So, but it's a different. Yeah. It's related. These things are related, but it's not the same. In fact, the proof of this approximate 0-1 law uses the Rousseau formula. Now Rousseau showed.
But it's a little strange that the hypothesis says a whole bunch of things are small.
Yeah.
The
So
conclusion is
intuitively
that
it
the sum
goes
of
in the
these
other
things is
direction.
large.
Indeed, intuitively it goes in the other direction. So how to apply this to get an alternative proof of part C here? Well, in part C, it was about pivotal sites, and I've left on purpose this drawing here to show what it means that V is pivotal. Now recall that our proof for part C was by contradiction, so we assume that we have an interval on which there's neither of the two percolation types takes place. But if neither of the two percolation types takes place, that means that the probability that this happens for a given V is small. Because V is either far away from this boundary or far away from this boundary. So in order to be pivotal, you must have a green path from V to something very far away. But since there is no percolation, this probability is small when n is large. So on this interval, we fulfill the assumption in this approximate 0-1 law, and therefore the derivative, according to the 0-1 law, is large. And so Rousseau pointed out in 1982 in this way that this combinatorial geometric stuff can be replaced by a more general theorem. But this more general theorem, so once you have it is nice, but the proof of this more general theorem, although it was in some sense elementary, but certainly it is not simple. So I'm not saying that by this you get really a simpler self-contained proof. Now some more remarks is that I think that for a while this Rousseau approximate 0-1 law, it did not get much attention, but later extensions and generalizations came up, and I want to mention one by, well, there are lots of them, maybe I should not write down but mention them to save time. So there was Kahn, Kalai and Lineal around 1988. And so that was a more precise and more quantitative statement than Rousseau's approximate 0-1 law. And what I will, and then there was Friedgut and Kalai in the late 90s, I think, which was based on this. So this was from 88, I think. So Friedgut, Kalai was late 90s, I think. More recently, Bolabas and Riordan used these Kahn, Kalai, Lineal, and Friedgut and Kalai things on. Pardon? Talagrand, that's the one I certainly want to mention because that's the one I used in my paper. Talagrand also has an explicit statement, and that's the one I'm going to write down, that's 94. He proved that the derivative of the probability of A is larger than or equal to some constant times the probability of A times 1 minus the probability of A times 1 over the logarithm, times the logarithm times the, maybe I should write it here, times the logarithm of 1 over the maximum over I of the probability that I is pivotal. So again, so this is more explicit because here you see that if all these I have small probability to be pivotal, so then 1 over this is big, so the logarithm is also big, and then if the probability of A is not too close to 0 and 1, then this product is large, and so the derivative is large. So this is a more explicit statement, an explicit version and stronger version than Rousseau's. And as I said some years ago, Bolabas and Riordan, they used Kahn, Kalai, Lineal, Friedgut, Kalai stuff for percolation. I think they were not aware of Rousseau's approximate 0-1 law. But they also they have a famous paper where they apply these kind of 0-1 laws, or also called sharp threshold results. They applied it to Voronoi percolation, and I'm almost I even don't have time. I almost have no time to state my own result now.
Very quickly, so that's an absolute constant, is it?
That's an absolute constant, right? Yeah.
And this is in the generality of just a whole bunch of 0-1 random variables with probability p and
product
any increasing
measures.
event.
Product
measure and
measures.
any increasing event.
Product measures increasing event 0-1 to the n, in fact.
Right.
Yeah. So last year I asked myself the question: can I use these kind of things, and in particular Talleyrand's inequality? Can I use that to make Higuchi's result for the ising model smoother? And I did not even say what this ising percolation model is. I cannot write it down, so let me say in words. So you have ising model with a parameter beta. We fix beta smaller than the critical beta c. But then we have another parameter which is called external field, h. And that's the parameter of our model. And it can go from -infinity to +infinity. And Higuchi's result in some sense says that when you vary this parameter h, then we see the similar behavior as in this classical percolation model, namely that for h small, you see star percolation of minus, then for h above the critical value, you do not see that, but you see the ordinary percolation of pluses. And as I said, he used those classical techniques of Harry Kasten. It became very messy because of the dependencies, and I asked myself, can I make that nicer by these approximate 0-1 laws? And then the problem is, of course, the dependence. This is done for independent random variables. So what I did is I looked at the dynamics for the ising model, and since beta is smaller than beta c, you have a rapidly mixing Markov chain that was proved by Martinelli and Olivieri in the early 90s. And then I represented Markov chain by space-time variables xvt, and these are IID, and they kind of tell you what the updates of the Markov chain are. So at time t you want to update v, and then you look at the number of pluses and minuses of this v, and then you compare it with xvt, and then you say if it's smaller than xvt, then it becomes plus, and otherwise it becomes minus. So in this space-time picture, we do have independent random variables, and to those independent random variables I applied Talleyrand. And then you have to be a little bit careful, because now you have to deal with the pivotalities of these variables, and that's not exactly the pivotality, the original pivotality. So you have to make some translation, but then using this fast mixing, things work out well. And here I really have to stop. I'm sorry that I already used more time.
Thank you so much for this nice talk.
How this H critical depends on temperature, and what happens at H critical?
At H critical, there's neither plus percolation nor minus star percolation. That was also known already by Higuchi.
How it depends on the temperature, this H critical?
That I cannot say much about.
You don't know if it's monotone.
Well, if beta is 0, then you are back in the, then you are roughly back in the ordinary percolation model, right?
You don't know whether turning on the positive correlation helps the percolation, so that you have to make H more negative to suppress it.
I don't know, actually. It might be known, but it's not so simple, because it helps. If this intuition is true, it would also help the minus star percolation.
Rousseau's theorem says that at PC you have no green percolation and no star percolation. What you wrote down as equivalent doesn't quite, I think, deal with that case, or does that property at the critical point follow from other methods?
Yeah, that follows from other methods. I had to focus on certain aspects.
For any of these sort of systems, there's some general principle that says that.
Well, under certain conditions, yes, under certain conditions. Actually, also stronger properties are known than what I know. So if P is smaller than PC, there's no percolation of green, I wrote there, but you even have exponential decay for the cluster size distribution. That also holds for the Ising model. And, but once you have the other things, then from the proof of the other things, this exponential decay follows relatively easily. So not from the statements, but from the proof of the statements.
Any other questions? Okay, so we thank the speaker again.